So if you haven't already started the homework, that's okay. It's not due until Monday. It is 1.5 homework, and there's going to be some questions in which it's going to ask you to transform where this point went to. So the point is 3, -2, and we're trying to determine where it's gone to with these transformations. Now, if it is outside of the function, so you don't see it inside these parentheses here, because that's how we're defining the function, then, oh, sons of guns, just give me a minute. It did that to me earlier today, so give me a moment. So if it's not within those parentheses, it does the range. So if you recall from our transformations, we have g of x is equal to a f of b of x minus c plus d. Oh, this is not going to be These two are within my function, so they mess with the domain. That means that it's going to change the x values. And these two are outside of my function. They're outside of that f of x. So a and d are outside of my function notation, so those mess with my range or my y values. And when it's my range, it does exactly what I expect. When it is in the domain, it does the opposite of what I expect. So I look at what I have, and this is A, so that's going to mess with my range. And this is D, so that's going to mess with my range. So if I come down here and I do the first one, I take my ordered pairs one more time. We have this point 3, -2, so 3, -2. And what we're going to do is we're going to transform it, and the first thing we're going to do by our order of operations up here, I have the points in which I'm going to do this is I'm always going to do this one first. Okay. Let me see. So with the order of operations, when we're doing transformations of graphs, then I want to do B first. Then I want to do C if I have it. And then I want to do A if I have it. And lastly, I want to do D if I have it. So if I don't have any of those, I can just skip through it. So let's take a look at our example here. I have 4 and I have -1. So that 4 is A. So I don't see a B and I don't see a C. So I'm going to do that 4 first. And what's going to happen is that I'm going to take all my y's and I'm going to multiply all my y's by 4. So it's going to be 4 times y. My 3 does not change, so I have 4 times -2, which gives me -8. So let me do that in a different color so you can see that I have done that transformation. That becomes -8. -2 times 4 is -8. And then the next one I want to do is I want to take my y values and I want to subtract 1 from it. Notice that my x does not change during this. It's just the y, because my 4 and my -1 are in the range changing. They're the vertical transformations, not the horizontals, so it's going to change my range. And so my point -8, I subtract 1 from it, and I get -9. Now let's take a look at number 2. I got to figure out what I have. So if I look at number 2, and I compare it to my transformations above, this -3 is B, and this +1 is C. So these are missing with my domain. They're going to change my domain values. That means I'm going to be changing my x values. And so for number 2, I take my point, which is 3, -2, And if you remember, when it's inside of my domain, it does the exact opposite of what I expect it to do. So I would have expected to multiply by -3, but instead I'm going to take my x, I'm going to divide by -3. This is messing with my domain, not my range, so the -2 doesn't change. I take -3 and I divide it into 3 and I get -1. The next step I'm going to do is my +1, and I want to think of it as +1, but remember it's inside my function, so it's going to be x minus 1. Again, my -2 doesn't change. My x does change, and so it is -1 minus 1 more, which gives me -2. So that's my final answer for this one. So here's my final answer for number 1, and here's my final answer for number 2. Now let's take a look at number 3 and look at each piece. This -2 is outside of my function. That is my a value from up above when I look at my transformations. This -1/3 is inside of my function. That is my b value. I don't have a c value, but I do have a d value. So that d value is -4. So first I mess with my domain. Again, my point starts with 3, -2. And I want to first take my x's, and I want to think of it as the opposite of what's happening. So I would have been dividing by -1/3. So in other words, the reciprocal of that, multiply by the reciprocal of that, which is multiplying by a -3. So I'm going to take my x's, and they're all going to be multiplied by -3. My -2 is not being changed at this moment, but I am multiplying my 3 by a -3, which gives me -9. So now that I've done that, I'm going to come outside, and that means I'm going to multiply by the y value. So -9 is not changing, and my y value is going to be multiplied by -1/2. So I'm going to take -1/2 and multiply it by y. So when I take the -1/2 and multiply it by my y value, I'm going to get a +1. The last thing I'm going to do is I'm going to take my y value and I'm going to subtract off 4. So it is y minus 4. Again, my -9 is not changing, and what is changing is I'm going to take 1 and I'm going to subtract 4, which gives me -3. And so there's my final answer for that transformation, and that is a parenthesis, not a bracket. Okay, so now let's get to what we were doing today. What we are doing today is the absolute value functions. We're going to transform these, we're going to graph these, and we're going to find the x and y intercepts. So when we're doing the absolute value function, basically what's happening, if you remember this is one of our parent functions, is it's saying on the right side, it's like a piecewise, on the right side of 0, the line coming out of it is the line y is equal to x. So it's going to have a +1 slope, and it goes through the origin. If you're on the other side of 0, then it is the slope, or it is the equation y is equal to -x. So in other words, it still goes through the origin, but we have a -1 slope. So that is what we're graphing today. It is our parent function, which is the absolute value, and we've talked about this a couple of times. And then this question that we're going to ponder is, do I always expect 2 answers when I'm solving? So I'm going to pause this and give you a moment to think about it, and then we'll go over it. And the answer is no. There are times when I have the absolute value of a. If b is 0, I'm going to only get 1 answer. If the absolute value of a is equal to a negative number, say -3, then I'm going to get no answer. So it's a no solution. So this has 1 solution, and this has no solutions. So I'm not guaranteed 2 answers when I have it set to absolute value of a is equal to b. If b is 0, I get 1. If b is a negative number, I get none. So if I'm asked to find the x and y intercepts of an absolute value function, then all I'm really doing is I'm going to let x equals 0 to find the y-intercept, or I'm going to let the function equal 0 to find the x-intercept. So when the function is set equal to 0, find the x-intercept. So if I come down here and I'm asked to find the x and y intercepts, then I can do this by setting let x equal 0. So if I let x equal 0, I'm going to be finding the y-intercept. And I'm guaranteed a y-intercept. I'm not guaranteed x-intercepts. So y, or f of x, is equal to the absolute value of 0 minus 3 plus 1, which is equal to the absolute value of negative 3 plus 1, which is equal to 3 plus 1. So in other words, this is 4. As an intercept, remember intercepts are always ordered pairs, it'll be 0, 4. Now let's do the y, or the x-intercept. So to do the x-intercept, we have the absolute value of x minus 3 is minus or plus 1 is equal to 0. The absolute value of x minus 3 is equal to negative 1. And we just talked about how this is a no solution, because you can't have an absolute value equal a negative number. So that tells us there are no x-intercepts. Now, we could have done this also by transformations. So remember, my parent function of an absolute value is going to look like this. And the transformations are, I'm going to go up 1 and I'm going to go right 3. So I'm going to take this point, go right 3, 2, 3, and up 1. And I can see by graphing it, I would not have got any x-intercepts. So let's take a look at our next example here. And just looking at the fact that we have a plus 2 here, we already know we're not going to have any x-intercepts. So no x-intercepts. Okay, so all then we have to do is find our y-intercept. So let me give myself some room here. I'm going to erase this. I'm going to find our y-intercept. So with our y-intercept, what we're going to do is we're going to say, okay, let f of 0 equal. So 2 plus the absolute value of 3 multiplied by 0 plus 1. This is going to be 2 plus the absolute value of 1. So this is going to be 2 plus 1, or in other words, 3. So my x-intercept is 0, 3. And I could do that by also graphing it. Now for this particular graph, let's just talk about this graph. This particular graph, I have to put it in the correct form. Right now we have f of x is equal to 2 plus the absolute value of 3x plus 1. We talked about when we have g of x has to be my a, f of b, x minus c plus d. Now what I see here is this 3 is b, but to be in the correct form, notice how b is factored out and off of the x. So let's just take a moment to put this in the correct form. So f of x is equal to 2 plus the absolute value. So I'm going to factor out a 3. So in other words, I am dividing both the x, the 3x and the 1 by 3. And so there, now it's in the correct form, and I can see the transformation. The transformation is it's going to be compressed in the x direction by 1/3, and it's going to be moved to the left 1/3. It's going to be moved up 2. Let's take a look at our last example here. We'll start with the x-intercept, or excuse me, the y-intercept. So to find the y-intercept, we're going to let x equal 0. So f of 0, 3 absolute value of 0 plus 5 minus 1, which gives us 3 the absolute value of 5 minus 1, which gives me 15 minus 1, or in other words, 14. So my my y-intercept is 0, 14. Now if I take a look at the fact that I have a transformation here, then I know with this particular transformation, because I am moving down 1 and I'm still opening up, then I'm going to expect this to have an x-intercept. In particular, if I take my parent function, which looks like this, my transformed function is it's going to go left 5, it's going to go down 1, and it's going to have a vertical stretch by 3. So using this information, I'm going to go left 5. So here's about negative 5. I'm going to go about down negative 1. And then it's going to be much steeper. So my slope coming out is going to be a 3, 1. My slope coming in is going to be a negative 3, 1. So it's going to be a lot steeper. So that's about what it looks like. So I know I'm going to have x-intercepts. So let's go ahead and find my x-intercepts. So my x-intercepts are, I do 3, the absolute value of x plus 5 minus 1 is equal to 0. When I'm finding my x-intercepts, I set it equal to 0. So 3, the absolute value of x plus 5 is equal to positive 1. And because it's positive, I know I'm going to have 2 solutions. The absolute value of x plus 5 is equal to 1/3. And if you remember from yesterday, we have to try to isolate the absolute value. And so this, let me just erase this over here. And so what we end up with is we have x plus 5 is equal to negative 1/3, and x plus 5 is equal to positive 1/3. So x is equal to negative 5 1/3, and you can turn that into its decimal equivalent or improper fraction, or you can just leave it like that. And then x is equal to, and I have negative 5 plus 1/3. So in other words, I'm going to have negative 4 2/3 is my other x part. So my ordered pairs is negative 5 1/3. So negative 5 1/3, comma 0, because these are always ordered pairs, or negative 4 2/3, comma 0. All right. So the questions to ponder here is, if we couldn't observe the stretch of a function from the graphs, could we algebraically determine it? And then the other one, do the graphs of absolute value functions always intersect the vertical axis and the horizontal axis? So I'm going to let you contemplate that. Let's take a look at these 2 applications. Cities A and City B are on the east-west line. Assume that City A is located at the origin. The distance from City A to City B is at least 100 miles, and x represents the distance from City A to City B. Express this using absolute value notation. So the first thing I'm going to do is I'm going to draw the graph. And City A to City B, here's City A, here's City B, City B. And they tell us that they're on the east. City A is at the origin, so let me move that to where it needs to be. So here's City A. It's right here at the origin. And they're on the same east-west line, so that means that we are going left to right. City B is, the distance from City A to City B is at least 100 miles. So this distance is at least 100 miles. So this is at least 100 miles. The distance here is at least 100 miles. But it doesn't tell us where B is. It could be on the left or the right of A. So it could be back here. In this case, it would be X, this distance. This distance is still 100 miles. So what that means is, if we let x be the distance between the 2 points, the absolute value of x has to be greater than or equal to 100, because what I want is I want this value of numbers on the outside of 100, because it says at least 100 miles. So if I have at least 100 miles, then I want the distance, the absolute value of x, to be greater than or equal to 100. Let's take a look at this one. A student who scores within 18 points of the number 82 will pass a particular test. Write this statement using absolute value notation and use a variable x for the score. So the student needs to score within 18 points to get at least an 82%. So x is the person's grade. Because it says it wants to score within 18 points, So I want to have this range of scores of 18-point difference from their grade. It's going to be x minus 82, absolute value, is less than or equal to 18. So, in other words, if the person scores within 18 points, we're all good to go. So if I were to check this to find out what their scores are, we have negative 18 is less than or equal to x minus 82, which is less than or equal to 18. And then I would just add 82 everywhere. So plus 82, plus 82, 82. And if I add 82 everywhere, I'm going to get my calculator out because I can't always do this off the top of my head, especially days like today. So 82 minus 18 is 64. And less than or equal to, that one I can do is 100. Okay, so 64 to 100 is a passing grade for this particular test. And so as long as their score is within that region, then they are going to be passing this test. Now let's take a look at some graphing. We've already talked a little bit about the transformations of graphing, so let's just come down here and do some more graphing. And so we remember that our parent function, I'm going to draw this in black, is from the origin. It comes out as a 1, 1, and it comes into it as a negative 1, 1 slope. So that's my parent function. So again, I'm going to go back to g of x is equal to a f of b of x minus c plus d. Now, for this, I'm going to look to see what that negative 6 is. Well, that negative 6 represents the c. So that means it's going to mess with my domain. It's going to change my domain. And we know that when it's inside of our house, it does the exact opposite of what we expect it to do. So it's actually going to pick this graph up and it's going to move to the right 6. So here's where it's going to be where I come out. So the origin, the point 0, 0, gets moved over to the point 0 or 6, 0. And then I'm going to come into it with a negative slope. And so there is the new graph. Let's take a look at B. Now, I'm going to start from the inside, and we know from what we were looking at from before, the previous example, is I need to get this 2 off of the x. I need it to be in this form right here. And it's not in that form, so what we're going to do is we're going to go ahead and factor out that 2. So negative 2, and then I'm going to factor off the 2. So in other words, I'm going to divide both 2x and 4 by 2. So x plus 2, and then minus 3. Now that it's in the form that I would expect it to happen, which is I have my b value factored off. Now, I'm going to do something slightly different. Absolute value functions, if I see that this, like my lightsaber, I love it. So I see that that 2 is positive. I can pull the 2 out of the absolute value function without changing anything. So negative 2, absolute value of x plus 2 minus 3. The only reason I did that is so that for me, it's easier to see a vertical stretch than it's going to be to see a horizontal compression. So in this case, because it's the absolute value function, the horizontal stretch and the vertical compression frequently can be the same thing. So a compression by 1/2 is if I would have left it inside there. So if I would have left this inside here, but I would have left this 2 inside, that 2 would have been a compression by 1/2, but bringing it out, it does a vertical stretch by 2. So in this particular case, this 2, which is a compression by 1/2, equates to a vertical stretch by a 2. Negative just means it reflects over the x-axis. So again, I'm going to draw my original function. So it comes out like this and like this. And then the transformation here is this negative is going to reflect across the x-axis. The 2 is a vertical stretch by 2. This 2 here, let me do it in the correct color. This 2 right here is a horizontal translation. So that 2 means we're going to move to left. And then this negative 3 means we're going to go down 3. Okay. So let's move our point. Our point that we should have is 0, 0. It is going to move left 2, so I'm going to go here, and then I'm going to go down 3, so I'm going to go down 3. So that's where that 0, 0 went to. So 0, 0 went to the point negative 2, negative 3. Now, it is going to have slopes of negative 2 and positive 2. So this time it's going to come into this with a negative 2 slope, and it's going to come out with a positive 2 slope. So that's what that particular graph will look like with the transformations. Here's a couple of questions to ponder. Is it possible, if possible, find all values of A such there are no x-intercepts? Now, we take a look at this, and what we see when we are moved up, when we don't have a reflection over the x-axis, if we don't have a reflection over the x-axis, then all I have to do is move this up. So as long as A belongs to, that's element belongs to, between anything larger than 0 to infinity, I'm going to have no x-intercepts. So as long as A is a positive number, because I don't have to worry about any kind of reflection, as long as A is a positive number, this thing is just going to move up. And you're never going to have any x-intercepts. And this is not possible, because I'm always going to have a y-intercept. Unless I restrict my domain, I'm always going to have a y-intercept. And that's it. That's 1.6 put to bed. Hope you have a great weekend.